going. Okay, so decay can be alpha decay. This is atomic decay. It can be alpha decay, which is a alpha particle leaving, or it can be beta negative decay, which is an electron. And because this electron comes from a neutron, it creates an electron and a proton. And so you add one proton, but you've lost an electron. So the mass is the same. You just go up in atomic number by one. And also there's an anti-electron neutrino. Yes, Kenta?
Doesn't the electron not matter in the atomic mass?
Yeah, it doesn't.
Then why'd you say that because you lost an electron, the 14 stays the 14?
You lose a neutron, but you gain a proton.
We just didn't write
So the mass stays the same. Did I say electron?
No, I don't really know.
You lose a neutron, you gain a proton, the mass stays the same. The electron's just shown because it's what flies off, right? That's the particle. And you also have to have an anti-electron neutrino, which we will learn a lot more about soon. You can also have a beta positive decay. This is a positron, which is the antimatter particle of an electron. Almost always the antimatter particle has a line drawn over top. This is the only one that's not, just because they want to make your life difficult.
Should a neutron be set on the beta decay or no?
No. So this is a positron, which is an anti-electron. Okay. And that's going to provide us with what? So the positron comes from a proton becoming a neutron and a positron. And so we're going to go down atomic number here because we've lost a proton. So this becomes fluorine. Sorry, there's a plus here. This becomes fluorine, which is 9, but the mass stays the same. So this is kind of the reverse of what happened before. And we'll go through all this because when we do quarks, this will make more sense. And we're going to have fluorine. And then we also have to have, because we made an anti-electron flavored particle, we also have to create a matter particle of that same flavor. So, but we don't have enough mass to make an electron. So we're going to make an electron neutrino. But this is not an anti-neutrino, it's just a neutrino. Neutrinos are very small, uncharged. There's neutrinos going through you right now that you can't sense.
So is the other one anti-electron neutrino?
Yes. Yeah, this is an anti-electron neutrino. This is an electron neutrino.
And the possible is what?
Positron.
And what's the opposite of?
Electron. But it doesn't have the line. It's just convention. Yeah. Okay. Things fall apart and you need to know a bunch of math to do with their decay rates. Okay? So if you want to know the number of nuclei that you have left out of a sample, that will be equal to the original number of nuclei times E to the power of negative lambda T. So let's just label these. Sometimes this is N of T, so we could just say number of nuclei. Yeah, well, I buffered in a few minutes of nuclei. Number of nuclei at time T. Set it for 5 minutes. Give me 5 more minutes. N naught is original. Number of nuclei. Oops, sorry. E is Euler's number. Should I label that? I guess so. Do you guys know Euler's number?
Yes.
Who said yes? Who says no? Yeah, this is 2.718, right? 718.
Yeah. It's E, the calculator.
Yeah, it's the calculator. Yeah, it's E. These little symbols are very important. This, well, T is just time, but lambda is the decay constant. This is the probability of decay within a set time. Oops, off the edge. And of course, this is just time. This is because, so you guys who are SL, you don't know this. HL, this is review. So if I give, this was Hamid. Hamid wanted to be rich.
Right.
Can I go into that again?
Yeah. So I gave $1 million to Hamid, and Jeffrey is poor and he needs money. Pay for his university because he's gonna get a PhD and win the Nobel Prize, and he needs money first so he can go to school. So he borrows $1 million. That's the type of guy he is.
Says a lot about you.
You see what I'm doing here? This is ridiculous. Oops. Story of my life. Jeffrey is gonna borrow this $1 million from Hamid, and Hamid is going to charge him what percent?
15.
Let's say 50.
Oh, I'm being ripped off.
Hamid's a baller, yo.
It works.
She's like, look,
Sometimes there's
if I'm lending this out, I want a real return, so I'm gonna charge you 50%. So at the end of the year, how much does Hamid get back? 1.5 mil, right? The next year, Jeffrey says, okay, can I, he pays her the 1.5, he's like, I want to borrow $1 million again. She says, okay, I'm going to lend you $1 million, but now, oh, and I'm off the video. I'm going to lend you $1 million, and I'm going to charge you 50%. But this time, I'm not going to charge you just once, I'm going to charge you twice. So go on your calculator, put in $1 million, and go times 1.5. But then you can't charge 1.5, right? Because she's doing it twice. She can't just do it twice. But she can charge half of the 50% twice, right? So you're gonna go 1 million times 1.25 times 1.25. Yes?
Yes.
Okay. So what you're really doing here, and it's going to be a little bit more than 1.5, is that right?
Yes.
Because now after the middle of the year, she's charging the 0.25 on a little bit more than $1 million, right? So what you're really doing is you're saying, I'm going to do $1 million times 1 plus your borrowing rate, right? But it's going to be the rate divided by your time, right? And then to the exponent of your number of times you compound. So if the next time he borrows the money, she's gonna be like, I'm gonna charge you every month. And then she's like, screw it, I'm gonna charge you every second. I'm gonna find the number of seconds in a year, and I'm gonna divide 50% by that number, but I'm gonna times you that many times. If she keeps doing that, it will not be infinite. It will go to E. Oh, it's that time. I wonder if that's going to be in the video.
Almost certainly.
What?
Almost certainly.
Oh, that's the time. I thought it was like an emergency or something. Okay, I'll try. I'll try hard. Okay, so The maximum interest you can do is an infinite number of times, and that means you're going to times by e to the power of t. It's 2.718. It just doesn't get any bigger than e. That's as most you can do. Now, because with nuclear decay, you have a lot of nuclei, right? And you have an infinite number of time periods in which those decays can happen. It's an Euler's number formula. If you go to Desmos, you can type in y equals e to the power of negative x. And you will get a function that looks like this. This is your decay function. You start at 1, right? And I would encourage you to do this yourself and play around with this. The cool thing about Euler's function is that it is its own derivative. So if you look at the slope here at 1, the slope will be 1. It's negative, but because it's negative x, but it's negative 1. If you go to where it's 0.5, your slope will be 0.5. Okay. And that's cool because we can use it mathematically. Your half-life formula, maybe I should just draw this on the board. I'm trying to do an hour's worth of teaching in 5 minutes. So you have n equals n naught e to the negative lambda t, right? So if I give you if you can find the original number of nuclei and you know the time and the decay constant, you can find out how many nuclei you will have left. Okay? If you want to find out when is the half, because you can't find out when it's all gone, right? It will literally take forever. Not in reality, but it takes a long, long, long time and it's meaningless. But you can find out when half is left. So when half is left, what you've got will be half of what you started with, right? So it's really just 1 equals 2 e to the negative t, but I'm going to replace t with h because this is my half-life. So you don't talk about radioactive materials in terms of their lifetime, you talk in terms of their half-lives. So this is the time it takes for half the material to disappear. So this is 1/2 equals e to the negative lambda h, yeah? Okay, so we're gonna ln it, right, Eric? Good. So we're gonna ln both sides. And we have ln of 1/2 equals ln of e to the negative t, right? This is ln of 1 minus ln of 2, right? What's the ln of 1? 0. So this is negative ln of 2. And this, you can just bring this part down, right? Yeah. This just goes down here and this disappears. So this is just negative lambda h. You agree? Sorry, this t is supposed to be h because this is half-life. The negatives go away because they're on both sides, and so you have the ln of 2 over lambda is your half-life. Okay. So if you know the decay constant, the ln of 2 is 0.693, I think. Can someone confirm that for me? So sometimes people just remember the number, or you can just remember ln of 2 over lambda is your half-life. 0.693? Good. If you know the half-life, then you can find the lambda. What is lambda again?
Decay constant.
It's the decay constant, which means
Probability of decay.
probability that any nucleus is going to decay in a set amount of time. Sometimes the decay constants are in like per seconds. It's a really short half-life, it's per second. Sometimes it's per years if it's a really long one. Like U-238 is like millions of years. So it's like 10 to the negative 10, I think. It's like something times 10 to the negative 10 decay constant, because it's a really low probability of decaying in a year. Some things are way over 1 because they, like lithium 8 is like it's like 10 to the 9, like positive 9. So it's gonna decay like this, it's gone, right? Okay, Jeffrey, what?
So, we were discussing that the time in our universe is not continuous but discrete. So wouldn't it technically not be E itself? Different.
Yes, that's true. There is not an infinite number of time variables. There is a number,
Yes.
but it's a very large number.
So that's wrong.
Yeah, it's definitely wrong.
It's
Everything's wrong. A is activity. This is decays per second. Per second. Can they see this on the movie?
Yeah,
Yeah, barely.
Right, just about, yeah.
Okay, that's fine. Because the activity is related to the number of nuclei, you can also say that A equals A naught e to the negative lambda t. And then we can relate the decay constant with A and number of nuclei as well. Yes?
Well,
Blah, blah.
okay, the decay constant is the probability of decay for a set amount of time, right?
Yeah.
Isn't this like, is this A value, is it like the one where you already apply the probability to it? Or like, no?
A is dependent on how many nuclei you have.
Okay.
So, for example, let's say you have, can I erase this? It's on video anyway, right? Now I'm gonna have a lot of videos to upload. Let's say you have a rock. This is a rock.
Yes.
And the rock has 100 nuclei in it,
Okay.
okay? And its decay constant is 0.5. No, let's say 0.1. So there's a 10% probability of any nuclei decaying. How many nuclei are you gonna have after 1 second?
Well, is it in seconds or?
Yeah, let's say this is 0.1 per second. How many are you gonna have after 1 second?
99.
Probably 99, right? But after that, it gets a little different, right? What about when you have half? What then?
Wait.
49. Oh, no.
But it's not quite 49, right? There's a 50% chance in the next second. Does that make sense?
Yes.
Am I doing that right?
Because the amount is smaller, the probability of one thing that decays gets bigger.
Let's try this. It's 0.1% chance, right? So if 0.1% of this decay,
1%.
you're gonna have, no, not 0.1%, sorry, 10%. 10%. So you're gonna be left with 90, right? After a second, about. I think I was doing 1%.
Yeah.
Sorry, I'm trying to do this too fast. How much time do I have left? Is it already over?
Negative 5 minutes.
Ah!
Way over.
Way over. Okay, I'm sorry. We gotta get to the lab stuff. After a few seconds, if you started with 50, you wouldn't go to 90, right? You would be going to 45. So this is like, if you put a Geiger counter on this, you would be getting 10 decays per second, about, right? This is 10 decays per second, which you would hear in clicks. It would be like, grrr, right? And this one, you would have 5 decays per second, right?
So if the 100 after it goes to 50, so what does that mean? The decay per second goes down.
Yes, exactly. That's exactly what it means.
Why is the activity using the same formula as number of nuclei?
Because it's the same.
what is activity?
Your activity is based on the number of nuclei you have, right? It's related directly. So if you have half as many nuclei, Kenta, look at me. If you have half as many nuclei, you have half as much activity, right? So it's the same formula. But the decay constant remains the same. So the graph looks the same. It's just that remember I said that the E function is its own derivative. So as your number of nuclei comes down, your slope comes down the same amount. So your activity will decrease along with your number of nuclei.
Wait, but you said that when it becomes the 100 becomes 50, the lambda becomes 0 point or like. Oh no, it's not. No, never mind. Actually, yeah.
Lambda stays the same, but the activity decreases by the same factor that your nuclei decrease. Okay. Let's leave it at that for now. I'm gonna do some IA stuff with you.